Hello, everyone. My name's Joe Tyler. I'm an AI researcher at Sonar. And today we're going to be talking about SonarSweep, which is a tool we've been researching and developing that will help to improve the quality of AI output. So we're speaking at a time where AI tools are being adopted across enterprise teams. They're not just for people experimenting with new workflows. And therefore, it's important that when you're using these new AI tools across your enterprise, that you're not building up masses of technical debt, and you're aware of the quality of the code that your AI is generating. Even in the case that your AI models are generating good quality code, it can take several iterations to make sure that it's free of bugs and vulnerabilities. And today we're going to look at why that happens, why LLMs generate these vulnerabilities and bugs, and how we can fix that at the source. So searching for new improvements to LLMs, and especially their coding abilities, is a very relevant topic. This is a quote from Ilya Sutskever, who is a prominent AI researcher and co-founder at OpenAI, although now he's moved on. As he says, the 2010s were an age of scaling, and now we're looking at what's next. How can we improve our AI, improve our large language models without using more data? And this is a question that made us think. If we can't scale up the amount of code used anymore, how can we improve the data and training processes for making expert coding large language models? And can we build the insights and our knowledge of static analysis and code to build better AI coding? So to develop this idea further, I'm going to introduce the concept of garbage in, garbage out. In AI code generation, this is a significant hurdle. Foundational models datasets can be a pretty chaotic mix of really good, brilliant engineering patterns, and also contain bugs and vulnerabilities. And in the training process, LLMs aren't taught about these subtle patterns. They are just taught to generate the most likely tokens, the most likely completions to each prompt. And therefore, if there are bad coding examples in your dataset, an LLM might inadvertently learn to generate a vulnerability or some bug in your code. And this idea was made clearer to us when we and reinforced when we saw that Anthropic had released research in October showing that large language models trained on datasets that contain even a small, constant number of bad, low quality poison data, this can lead the model to include a backdoor, so that a malicious actor could give it a trigger prompt that will cause it to, code a vulnerability in your code base. And this brings us to SonarSweep. So the idea is that we treat these training datasets as not just raw text, raw code, but as critical software assets, because there's a direct impact from what's in your training data to what will come out in your large language model. And we leverage our deep expertise in static analysis to maximize your data quality and make sure that that data processing is done in a code-aware manner. So not looking at the raw code, not looking at the raw text, using our static analysis tools to curate and make sure you have the highest quality data set. And this is done in a few stages, which I can talk you through now. So we start off by analyzing the code. We make sure that your data set is free of duplication. And the analysis will tell us where the bugs, vulnerabilities, and code smells exist in your data set. Then we can apply Sonar's code remediation capabilities to programmatically patch these issues. And this makes sure that the data remains accurate, but also the training signal is rich. So there's a lot of really good patterns for your large language model to learn from. Finally, we do a final layer of data processing. We deduplicate the code again, We make sure that anything that is still low quality after we've tried to fix it is gotten rid of. And then we make sure that the dataset is optimized for diversity by sampling across different topics that you want your large language model to excel at. And finally, we've trained a few models based on this pipeline, and I'm going to talk you through what we found out. So to measure if this methodology works, we have to make sure that we have metrics and measures in place. So typically for code generation, a benchmark will look like this. There'll be a task. It will ask the model to write some code to solve that task. And then you're going to run a load of unit tests to check that the code is doing what the task asked it to do. And this is what's done widely in benchmarks such as Human Eval, SweBench, and more modern coding benchmarks. At Sonar, we look further than this. So rather than just looking at how functionally correct your code is, we also want to make sure that it's high quality. And this is particularly relevant for code that's going to be deployed into enterprise environments. So which dimensions do we look at? We look at the security of the code. So is the LLM going to generate some code that could be vulnerable to a hacker to expose a data breach? How reliable the code is? Is the code going to be resilient under different conditions? Is it going to make sure that it's managing the memory, the efficiency of the system well? And then finally, maintainability. Is the code going to, it might solve the problem, but is it going to lead to long-term technical debt if it's difficult to read or hard to understand? And yeah, now we're going to look at what we actually found out when we did do the training on our models. So to start off, I'm going to show you what happened when we trained on some state-of-the-art models. So we fine-tuned 2 state-of-the-art models on a dataset of Java, which contained around 70,000 examples, which were diverse across different tasks, and we made sure that they did not contain any bugs or vulnerabilities. And here's what we found. So for Llama, which is a model from open source model from Meta, we found that the model that we trained generated 67% fewer vulnerabilities on our benchmarks than the base model. And we also saw a 32% reduction in the number of bugs. For GPT-4o, which is a closed source model, but we were able to fine tune it via the OpenAI API, we found that there was, we saw a 52% reduction in vulnerabilities, which is not as much, but we saw a greater reduction in the number of bugs. And both of these numbers are significant. And perhaps, like, most interestingly, even though we did this fine tuning and we saw improvements in the bugs and vulnerabilities, we also saw on the functional correctness benchmarks that there was not much change. And I think we even saw a slight improvement for both of these models. And this validates that even the smartest top-of-the-line models will still benefit massively from using high-quality sanitized training data. Yeah, and we wanted those models that we trained are large, not very easy to use. We wanted to make a demonstration that would allow people to get hands-on with what we've researched here. So we recently released a technical demonstration model of this methodology on Hugging Face, which I'll include a link at the end to download. So we took OpenAI's open source 20 billion model and we fine-tuned it on 70,000 Java examples again. And again, yeah, just to reiterate, this was a data set that was well balanced. We made sure it didn't contain any bugs or vulnerabilities. And yeah, we can see, compared to the original model, how it's performed. So this task is asking the large language model to perform a transaction on a database, and the base model has generated code which performs the transaction, but after it's completed the transaction, it forgets to clean up after itself. So it leaves some of its memory in use. This isn't going to immediately disrupt the program, but if you're performing enough of these transactions, it may lead to issues where your machine starts to run out of memory. On the other hand, our model, which we've trained on this clean, high-quality data set, has added these lines in green. So it's saying if at the end of your transaction, remove this variable, and that frees up the memory again. So using the model that we fine-tuned on high-quality code, it's going to give you code that's more reliable. And this is just one example. We see, I'm going to show you the metrics overall right now. So yeah, that was one of the bugs that we saw reduced. But in general, across the benchmarks, we saw a 41% reduction in the number of bugs seen, and the same exact number, 41% reduction in the number of vulnerabilities. And even though we weren't explicitly focusing on cleaning up code smells in this study, we also saw an 18% improvement in code smells. And again, we saw that the functional correctness of these models remained roughly the same. And we went further because we wanted to make sure that we weren't overfitting to code just for Java. And we ran a lot, we ran many benchmarks on this model. And we found that general intelligence as well as functional correctness remain the same. So that's like general question answering ability from just talking to the model. So yeah, with this, we can see that there's no like alignment tax is a common term. We haven't made the model worse at general abilities by making it better at code quality. And yeah, for more details about this model, how to download it, how to get started, there's a blog post on our website, and you can head over to Hugging Face to download the weights and have a look at the model card for more details about what we did. So to wrap up, if you're an engineering leader evaluating AI coding tools or fine-tuning models on your own private code bases, you must treat your training data sets as critical software assets. We've shown here data quality is a critical factor deciding whether AI brings you great value or introduces risk into your code base. Introducing bugs and vulnerabilities, code smells that could bring you security outages or bury your team in technical debt. And yeah, as I said, if you're interested, I encourage you to read our full research on the Sonar blog. And if you want to see for yourself, you can get your hands on the model over on Hugging Face with the link there. Finally, if you want to see how SonarSweep can improve output for your own AI coding applications, please sign up to join the Early Access program. The link to that is also on the SonarSweep product page on the Sonar website. Thank you for listening.